Humans have always admired the night sky. Ancient civilizations revered or feared the constellations and celestial objects as gods or divine spirits, orchestrating everything from rain showers and droughts to natural disasters and the commonly prophesied end of the world. Whilst these concepts were largely unchallenged at the time, people around the globe developed a working understanding of seasons, years, and the cycles of wandering stars, which we now know today to be planets. And from the time of Aristotle, the most widely accepted cosmological models placed our planet, Earth, firmly at the centre of the universe. These were known as geocentric models, the first proposed cosmologies of the oldest natural science, astronomy. Like all fields of science, astronomy has evolved greatly due to revolutions in technology and thought. The earliest astronomers recognized patterns in the motions of celestial objects, and by observing and predicting these patterns gave rise to astrometry. The Greek astronomer Hipparchus was probably the first to use mathematical astrometry when, by comparing the current locations of bright stars to those recorded by his predecessors Timacharis and Aristillus, he discovered the precession of the Earth. Though this was a remarkable discovery, over 300 years would pass before his work was further developed by the hugely influential Roman-Egyptian polymath, Ptolemy. The discoveries of Hipparchus were only the beginning for quantitative mathematical astrometry, which would become pivotal in the development of trigonometry, spherical geometry, and ultimately overthrowing the geocentric model. Ptolemy, however, would not be the one to challenge it. He was a strong proponent of Aristotelian geocentrism, and by combining a tremendous amount of ancient work, including that of Hipparchus, he produced the Almagest, or the Great Book. It consisted of 13 volumes and provided a mathematical model of the cosmos that would stand strong for over 13 centuries. In the Almagest, Ptolemy proposed that the Earth was at rest in the very centre of the universe, with the Moon, Sun, and 5 planets known in his time surrounding it. Further out in the celestial realm were the fixed stars, all moving together as a sphere. His arrangement for the celestial bodies was by far the most popular, despite alternate options suggested by Plato before him and others after him. However, like all geocentric models, it faced a significant problem. When we look at the night sky, we see the stars and other celestial bodies drift from the east to the west. This is formally known as diurnal motion. This is because of the Earth's rotation, or in the Ptolemaic model, the rotation of the heavens. However, periodically throughout the year, each of the planets in the solar system will apparently switch direction as viewed from the Earth and travel backwards for a while before switching again to resume their normal motion. To Ptolemy and his contemporaries, this retrograde motion was a very strange phenomenon indeed, but bear in mind that at the time, the planets were not known to be other worlds, but rather signifiers of astrological events, perhaps with minds of their own. Furthermore, no one had any concept of celestial mechanics governed by gravity or a working orbit theory. Ptolemy insisted, however, on a mathematical explanation. After all, the job of the astronomer was to make accurate predictions about the locations of the planets and constellations, so that astrologers could draw interpretations. To solve the problem, he adopted the work of one of his predecessors, Apollonius, from around 3 centuries beforehand. Apollonius had devised a system whereby planets travelled around circles called epicycles. Each epicycle then travelled on a much larger circle, called a deferent. Ptolemy further developed this by placing the centre of each deferent halfway between the Earth and a point he derived known as the equant. He recognised that this solved the problem of retrograde motion, despite the fact that he had contradicted the beliefs of his contemporaries that all heavenly bodies trace perfect uniform circles, because the resultant path traced by a planet in his system was an epitrochoid. But this actually solved another problem as well: the changes in the apparent distances to the planets. Ptolemy completed his model in a separate publication, his Planetary Hypotheses, after which he devoted his keen mind to other fields including horoscopic astrology. Despite his tireless efforts, Ptolemy's attempt to fit his observations to his assumption of a geocentric universe is considered an example of bad science, Nevertheless, with only a few minor alterations throughout the centuries, Ptolemy's model would stand triumphant until the Renaissance and the work of a Polish astronomer by the name of Nicholas Copernicus. In 1543, after over 3 decades of work, Copernicus published his magnum opus on the revolutions of the celestial spheres, 6 books in which he presented the first scientific heliocentric cosmology, that is, with the sun at the center of the universe. Though he was certainly not the first to postulate heliocentrism, citing the work of Aristarchus, who preceded him by over 1200 years, his much more scientific approach engendered a superior way of thinking about the universe. So began the Copernican revolution, although his work would gain little support for over 150 years because it made less accurate astrometric predictions than the Ptolemaic model. Copernicus had correctly identified that the apparent retrograde motion of the planets that confused Ptolemy and his peers was merely an illusion. Because the planets are in different orbits and travel at different speeds, we observe a parallax effect when overtaking them. This also applies when the inner planets, Mercury and Venus, overtake the Earth. It could be said that early acceptance of the Copernican model came about for the wrong reasons. Proponents of his theory liked his use of circular orbits in agreement with the still widely believed notion of the perfect heavens. But 50 years later, with the scientific revolution in full swing, the German mathematician Johannes Kepler was about to challenge it. Whilst working for the Danish astronomer Tycho Brahe, Kepler was appointed the task of studying the orbit of Mars. He had already developed an interest in Copernican cosmology, and he was troubled by errors between Brahe's observations of Mars and the orbit he calculated using the Ptolemaic system. He instead decided to try using non-circular orbits in a Copernican system, and after many failed attempts, he arrived at a shape he had previously thought to be too simple, an ellipse. 4 years later, in 1609, he published his Astronomy Nova, the New Astronomy, in which he presented 2 of his 3 laws of planetary motion, the third to be discovered a decade later. This would be another landmark work that would not immediately gain support. In fact, it was almost entirely overlooked, despite some independent verification from several astronomers. His most influential work would not be complete until 1621, the epitome of Copernican astronomy. It contained all his laws of motion, and after his death in 1630, it would enlighten many astronomers worldwide. In the same year that Kepler published the New Astronomy, a Tuscan scientist was familiarizing himself with a new type of technology for observing things at great distances by using the principles of optics that had been developed during the last 2,000 years. Galileo Galilei had been making alterations to his telescope, a design he adapted from that by a Dutch lens maker from the previous year. With this remarkable invention, he began to observe the night sky in a whole new way, and in January 1610, he discovered what we now call in his honor the Galilean moons, Callisto, Europa, Io, and Ganymede. At first, he believed them to be dim stars, but over several days he observed their motion and concluded that they were actually orbiting Jupiter. Many of his peers refused to believe him, as such a discovery was not consistent with Aristotelian cosmology. Later that year, Galileo went on to discover that Venus exhibited a complete set of phases, similar to the Moon. This was his single most important observation. Though it did not confirm the heliocentric model, it proved that Venus orbited the Sun. Perhaps then other planets might as well. Galileo faced tremendous opposition from the Catholic Church for defending Copernican heliocentrism, despite attempting to reconcile his findings with Scripture. He spent his last years under house arrest, but the seeds of doubt had already been sown. Heliocentrism would slowly claim its rightful victory over geocentrism. Galileo's methodical approach marked the true beginning of modern scientific astronomy. He is known as the father of modern science, the first to lay the foundation for the scientific method, favoring experimental verification over assumption and supposition. With the new scientific method, great physicists and mathematicians such as Isaac Newton, Joseph Louis Lagrange, and Albert Einstein would eventually develop the field of celestial mechanics, theories explaining the motions of celestial bodies in terms of their gravitational interactions. Today, the long-lived astrometry and relatively young celestial mechanics are united under the banner of astrophysics. And 400 years after the introduction of modern science, astrophysicists are exploring a universe stranger and more beautiful than any of the figures in our story could possibly have imagined. In the next episode, we'll begin to look at the size of that universe.